This video will be about the prediction section of a lab report. This is really the goal of a lab report, to try to figure out what will happen in the future. The goal of physics is to predict motion, and so this is kind of what the lab report is building toward. And it's the reason why you made your best fit equation in the lab. Because what the best fit equation is really doing is saying, if you do this to your IV, this will be the result for your DV. So we're going to see if those predictions come true. There are 4 steps to making a prediction. The first step is to just plug a number into your best fit equation to make a simple test prediction ignoring uncertainty. So you're going to plug that number in, ignoring all the uncertainties in your measurements and in your best fit equation, just to get a rough idea of what it's predicting. You're then going to do the same thing, but include the uncertainties. And because you're including uncertainties, you'll need to propagate the error in each measurement and come up with a prediction that includes uncertainty. You're then going to test your prediction and see if it's within the range of what your prediction is saying. And then finally determine if your prediction is interpolation or extrapolation. Basically, whether your prediction is inside the range of what you've already tested or whether it's outside of it. So I'll talk about each one of these steps. I'm going to use a best fit equation that I came up with in a previous video as an example. So let's say this is what you wrote down in a previous part of your lab report. And in the prediction section, your lab will usually ask something straightforward like, what is the position at time equals 3 seconds? So what it's asking you to do there is to just plug 3 into time, ignore all the uncertainties, and just carry out the math. So when I plug that in, this is what the equation looks like. And when I carry that out, I get that the position should be equal to 24.8 meters. So after 3 seconds pass, that should be the position. That's what this average best fit equation is predicting about the world. So step 1 is super easy. You just ignore the uncertainties and plug things in. For step number 2, the lab is going to give you a number with uncertainty, and it's going to ask you to plug that in and propagate uncertainty correctly so that you get one final prediction with one final uncertainty. So as an example, it could ask, what is the position at time equals 3 plus or minus 0.4 seconds? When I plug that in and propagate uncertainty correctly, this is what my final prediction looks like. The position should be 24.8 plus or minus 18.7 meters. Obviously, this is not the best prediction. There's a lot of uncertainty there, but this is just an example. So this is what I would call my data-driven prediction. It's data-driven because it was created by the data that I took from my lab that I graphed to come up with my average best fit equation. So this is what I would write in the data-driven prediction section. The test itself should determine whether the number that you get is inside of the range that your prediction is giving you. So my prediction is giving me a range of 24.8 plus or minus 18.7. So if I do a test and my number is within that range, then my prediction is correct. Finally, the 4th part is to determine if your prediction is interpolation or extrapolation. So interpolation means predicting something that will happen for an IV that's between other measurements that you've already taken. So if I've measured the position for the times 2, 4, 6, 8, and 10 seconds, and I then ask what will be its position at 5 seconds, 5 is within the range of numbers that I've already tested. So that would be interpolation. And interpolation should make you more confident about your prediction because you've already seen what happens when the IV is larger and when it's smaller. So you wouldn't expect anything strange to happen there. You wouldn't expect the IV to fail or the prediction itself to fail in some way. Just as an example of that, imagining that we're testing the stretch of a spring, and I've already tested the spring when it's stretching with less mass and stretching with more mass, and they both come out fine. I would expect anything in between that range to not break the spring, to not make anything strange happen like break or deform the spring. So that's why interpolation should make you more confident in your prediction, because you've already seen what your experiment behaves like for similar IVs. Extrapolation is when you're making a prediction about an IV that's outside the range of what you've already tested. Going back to my time example, let's say we've tested the position for time equals 2, 4, 6, 8, and 10 seconds, and I then ask, what is its position at 50 seconds? 50 is outside of that 2 to 10 range, it's way outside, and so that would be extrapolation because it's outside of that range. And extrapolation should make you less confident in your prediction because when you're outside the range of what you've already tested, other things could happen. It might be, as an example for the stretch of the spring, if you test a mass that's much larger than anything that you've tested before, it could be that the spring will break instead of just stretching normally. So you would have less confidence in your prediction because while your equation might be telling you one thing, something different might happen in the real world. So that's how you fill out the prediction section of a lab report.